Thank you, John Paul. This is the wording robotics, so I insisted that I want to come to this meeting and join the discussion. But I realized that this is a very dangerous field. Okay, I had a chance to start some big research at around 1998. It's a long time ago. And I was inclined to start something intelligent and something related to the brain and humanoid robot. So I tried to combine all of these. And we named the Robot Brain Project. So that is a field. And scientific point of view, I think that is a combination of symbols and mirror neurons and the human body. And philosophically, I could say that is a kind of, it's old philosophy about structuralism and the anthropomorphism. Well, I just want to use 3 slides to start what I was most interested in at that time. The Terence Deacon's book was so impressive, and he talked about the relationship between symbols, index, and icons. So it's just different levels of the abstraction. And also the relationship between language and symbol was also very exciting. And I didn't know how to handle this, but it is a very interesting field for me. Well, also when I was reading some books, the concept of mirror neurons are very stimulating. As you must know, some particular part of the brain of the monkey were activated when monkey saw someone else picking the nut. And also the same region activated in the same way when the monkey himself picking the nut. So the question was why single region has 2 different kind of the functions. So it is stimulating. So that area was considered as the motor speech center of the human brain, but there are very controversial discussions. Some people say there's no mirror neuron. Some scientists say there's a mirror neuron. So it's very controversial. But from computational point of view, it is very interesting hypothesis that the one computational mechanism can work to perceive the world and also to act to the world. So at that time, myself and my colleague were working on the standard robotics, kinematics, dynamics, and computations. So we have been working on how to efficiently compute the complex mechanical systems. So parallel computation and large-scale modeling, these are our field of work. Well, to start with, we decided to use the statistical model, hidden Markov model. Well, any statistical model could be fine, but using the statistical model, we can use for generation or recognitions. Statistically, we can tell the generative way or discriminative ways. It is well known now. And we called it the mathematical model of mirror neurons. So typically, we segment the motion, human motion, and then make the hidden Markov model, statistical model, and extract some mathematical parameters. And then we can use this set of parameters to recognize someone else's motions or different motions, or to create similar motions in both ways. So we called the set of parameters of hidden Markov model as proto-symbol. And naturally, between the statistical model, we can define the distance. So we can make the space structure between the symbols. So that was what we wanted to have. So having the distance, we can interpolate or extrapolate between the symbols. So this is very straightforward way, but the callback library information can be used for this kind of the distance. And this is, again, the very old story, but in our lab, we created some human motions, very simple ones, and created the mathematical model, Hidden-Markov model, and identified the distance and embedded into three-dimensional space. So we can interpolate between these points. Well, in the same space, by moving the point, we can create different motions. So actually, when he moves from walking to kicking, actually this red point is showing what he's doing. So by looking at the symbol space, we can tell what he's doing, or we can see the transition from one motion to the other. And from the moving the point, we can similarly create the robot motions. So we started this work. And of course, the idea of having mirror neurons was and is the communications, how the mirror neurons being used for communications. It's probably a big story or a long story, but I decided to make very short, simple stories. So okay. So this is the Hidden-Markov model we created from human model. But the robot has this Hidden-Markov model. And robot will see the human motions by his robot's own Hidden-Markov model and interpret the human motions. Of course, robot knows his own motions by Hidden-Markov model. Then in the higher level, we model the relationship between robot and human and recognize the relationship. The question is how to create the relationship. So this is an open question. But I just decided to just shortcut this one. That means that if relationship is good, let's keep the good relationship. If relationship is bad, let's keep the bad relationship. It's a just simple casual relationship. And if we eliminate unnecessary lines, the communication between human and robot becomes like this. This is very casual, design. And at around 2005, we had the Aichi Expo, and my student and small humanoid robot we developed did the communications. Actually, this is unfriendly communications. They are fighting each other. So they are doing something like boxing, and they are trying to hit their chest. And of course, the robot is 60 centimeters, and my student is tall. And of course, I want to protect the student, not the robot. Anyway, so this is a real-time fighting between human and robot based on the Hidden-Markov model. Well, since then, we further worked on how to nicely segment the motions, and also how to create the symbol systems, clustering and abstractions. And then we connected the motion symbol with words and language. What we did is very simple things, as you can expect. So I want to just show one after another. So this is the one of the automatic segmentation developed by my colleague, Professor Wataru Takano. So you can see the flash. That is the segmented point. So in this segmentation, we are trying to find out when the dynamics of motion changes. There's no explicit rules to cut the motions. We are looking at the dynamics of motion patterns. When pattern changes, we just cut. So in this way, we cut the motions automatically unsupervised way. And then we do the clustering. This is the example of nice clustering of all biological systems. So clustering is probably a fundamental way for human to understand the world. So I think we need the clustering. So, okay. So this is the result of the autonomous segmentation, automated segmentation. So the gray man is a segmented person. And the white one is the current movement. Actually, this is the famous radio exercise #1 in Japan. It's very typical motions. And then we have this kind of the data set. We classify the segmented data in this way, autonomously. And then we also have the sequence of motions data in this way. So this is the structure of the radio exercise #1. And maybe I missed something. Yeah. So assuming we have that kind of data, we apply the data set to predict the future of human motions. And this is actually the experiment. Oh, sorry. So again, this white person is a current movement of the person in front of us, and this radio exercise is already stored, and using that data set, we predict his motions, and this red person is one segment ahead of him. So one segment is typically maybe 2 seconds or about 1.5 seconds. So this is that's future. And this is 2 segments ahead of time. So in this way, for short range, we can predict the future of human movement. And Professor Takano, he is my colleague, and he recently moved to Osaka University and became a professor. And he worked on the semiology and he tried to connect the word or language and motions. And as everyone knows, that the natural language processing system is mostly designed or created by statistical mathematics. And our hidden Markov model and the natural language processing system is very smoothly connected. So we have motion symbol, we have wording, and we have latent state. So we try to learn the parameters between them. So this latent state is a state we need to learn or identify. So let me show. For example, we can create a robot motion from the sentence. So we create sentence and then create the typical motions for robot. Of course, this is not dynamically consistent, but we can create some reference motion pattern from the sentence. Okay, skip. Okay, of course, that is recalling the average motion pattern from the statistical model. but we can synthesize a new motion from the data set. This is some mathematics, but let me show the example. Maybe. So this is the very simple training motion just to touch the maybe my chest level. But we can modify the motion to touch lower level or higher level, and using the average data set. The computation is being done in the previous equations. So this shows the different motion data of particular joint. So by changing some parameters, we can change the motion patterns. Okay. More recently, the Professor Takano had obtained more than 200 hours of motion data by himself and by asking students. Actually, this is the X-sense suit with the accelerometer or gyros at the several points of the body. And he was wearing this suit for maybe at his own class or at the office or at home. So he created 200 something hours of data set. And he used the crowdsourcing to get those data annotated. So this is the result. So this is his office work. And from the annotated data set, the Hill-Markov model and the word and language set was created. And these are the most likely sentences that this motion suggests. Well, this is not being done in real time. It's quite computationally costly. So now he has over 200 hours, and that's much annotated data. It's quite a large data set. Okay, I'd like to show some of our students' recent work. Ikuo Kusajima, he's a PhD student of mine. He did this work at 2015 for his master's thesis. Sorry, it is Japanese, but since this is quite recent work, it's not translated just because of my problem. So the formulation is very simple. We have motion data set, we have document, and we have latent state, and then create the wording. But document is very large scale in this case. Okay, let me see. So he picked up the nearly 11,000 books from the copyright expired Japanese books. And that include the 291,000 paragraphs. So this document is one of those books or paragraphs. So using that, he created latent state. Actually, it's too big. So anyway, he tested different scales of latent state, and there were 111,000 words, counting only those appeared more than 5 times in those books. So he tried to create the latent state, and the idea is try to get some common sense or common wording from the books. It is very hard, actually. Our mechanism is so simple, so it is very hard. So, for example, if there is a love story, we want to have some nice sentences. But it doesn't work in that way. So anyway, for sentence association, we have the trigram and created them. So this is a scene that the housewife is cooking by fry pan, cooking something by fry pan. So there is the 50 sentences created in the order of the likelihood. So red one is those close to this original sentence. So first one and the second one, first one means a housewife is using fry pan. And second one is housewife is cooking. The third one is a housewife is cleaning windows. I don't know. Anyway, so well, this is the original sentence was that a person is rowing a boat, but in this case, the rowing boat is appeared only 6. The ones. First one is the musician is playing violin. So these are very different. Anyway, so then another student, Yoshihiko Yamada, he's also master student, worked on this work, and he tried to use different information about the object. Not only the motions, the knowing about object is very important. So not only the human motion pattern, he also included the distance between object and the body. And also object was recognized, those objects were recognized by the image information. And we use the Kinect for capturing the motion data. And the structure is same as the previous one. We have motion symbol and object symbol and latent state and wording. So basically the structure is simple. So in this case, actually, the performance is quite good. Of course, knowing the name of object, we can make much better the sentence creation. Okay. Anyway, so we worked on the symbols and the statistical model of the mirror neurons, and also the information about human body. Well, I didn't explain, and I don't think I have time today, but we have been working on neurobiomechanical computations. So taking the motion capture data, we can estimate the muscle activities, and also we built the supercomputing program for the detailed spinal neurons and the muscle models. And we collaborated with the brain scientists who had the Parkinson brain, and we combined 2 years ago. So the conclusion is very short. So we worked on words and sentence and related with human motions. Of course, we know that we need more information like object, or name of the person, or face recognition, or environment localization, whatever. But having those informations, we can make better and better sentence, I'm sure. And what is missing is that we can create short sentence, but storytelling is different one. I think we want to have some story, not just doing what now? If I, write my diary of the day, I would make a kind of story, right? Not just a sentence. So storytelling is probably the next stage we want to do. And if this is being implemented, what I'm dreaming, it's not dream, probably scientifically possible, is that robot will monitor its own behavior by language. Not just communicating, knowing the others, but robot himself can reflect himself by using the symbol system, what he's doing, or what he's doing to be considered by others, right? So interpret in many ways by linguistic association, and maybe he can, or robot can select a favorable story. Favorable means we can define if robot should be friendly to human, we can set to be friendly. And then robot may be able to modify or define the next versions. This is what we want to go. This is the Pac-Man, and I was playing last night. But probably this is the simplest way to make the storytelling. So, the relationship between human and robot or two other people are like Pac-Man, right? Going to friend or, avoiding the collision or. So I think the storytelling could be quite, for the deep understanding is difficult, but in the short way, we can make some kind of storytelling by looking at the Pac-Man-like game. Okay, thank you very much.
Comment, question? Yeah.
When I look at some of your examples and results, the sentences look like they match what's happening. And I wanted to reference the last thing you said, which is that deep understanding is difficult. And I always wonder, because I see examples of these kinds of matches, syntactic matches of words with an image or a video. And I wonder, do you think that this kind of research, this kind of matching with crowdsourcing can lead to deep understanding? Do you think other roads need to be traveled by researchers to get to deep understanding? Do you think deep understanding is not possible? I'm curious about the relationship in your own idea of research progress between what you do and the thing that is very difficult, which is for the robot or the AI system to actually understand the words it's using.
Well, mathematically possible, and I think we expected, but I don't think we did anything promising. But there are a lot of the text data that include the human culture, right? So somehow probably by doing this kind of effort, I think machine can create good sense of human life or human being. So I think it's possible by creating the knowledge of extracting the knowledge from the text data, novels or maybe webs or any text data. But of course, understanding the text data, we need a lot of the more preliminary, the mechanisms. So the reading the text is very difficult. It is also difficult for human children at the beginning, right? So once they can start reading the text data, I think that there are a lot of information in the world of text.
I would like to make a comment on that, and in some sense, your lexicon is based on a motion analysis.
Mm-hmm.
Then when you say that the guy is reading a book, okay, then this you refer to a special posture, okay, then a special behavior or a special body shape,
Mm-hmm.
okay, then which is the physical relationship
Yes,
between
yes.
the classical one between a book and the shape of my body in motion. But if I want, I can read a book like this, and in that case, you will recognize that I am reading a book. You see what I mean? All your symbols
Mm-hmm.
are based on the motion analysis.
Mm-hmm.
In some sense, this is a limitation.
Motion analysis. I'm not saying that only motions, but of course, the vision system or maybe other sensors.
Okay, this is why you
used.
are asking for annotation.
Yes.
Okay, to have a larger databases. Now, sorry, I made the confusion because you started from
we
the
started from
motion
motion
segmentation, and then, but after that you have to evaluate by.
We include object data, environment, and other sensing.
Okay.
That is necessary, of course.
Okay. You're okay.
There is another pioneer who works on this that use notations for the motion. You know, it's people that trying to organize, for example, music and put people dancing, for example. They have some kind of notations, and I think you are aware of that.
Yes.
So do you think that this is a middle layer before going to the interpretations that they are looking for? What you think, because I think in your system you try to go immediately to the interpretation. What is the scene, right?
So I'm a kind of structuralism. So I think it is very plausible mathematical or scientific assumption that biological system like human is trying to understand the world by simplifying the informations. So I think the understanding the world by discrete symbols is that kind of very natural mathematical hypothesis. So I think the Laban notation or language or whatever, that is a way how the complexity is simplified for biological system, not only humans, but so I think that is a middle layer. But of course,
you agree, right?
Yeah, I agree. That is the middle layer.
Other question, comment? No, people are tired. Okay, then thank you again.
Thank you very much.